for today. Um, so today we're going to study a new device, and this is the Mos transistor. So ito yung third electronic device that you're going to study this semester. No? So the first is the diode, the second the BJT, the third is the Mos transistor. Just to say a few things about the Mos transistor, this was actually invented after the BJT was invented. The BJT was invented in the 50s. The Mos transistor was invented in the 60s. So nauna talaga yung BJT. But right now, if you take a look at integrated circuits, most of the integrated circuits nowadays are composed of or are comprised of Mos transistor elements inside them. The BJT is not as popular as it used to be. But the reason why we study the BJT is because the BJT still has a lot of useful applications. And there are also certain applications na hindi pwede yung MOS na ginagamitan ng BJT. Okay. Ang una kong gagawin is I'm going to describe the structure of a MOS transistor. Now, this is not really part of the coverage of the course. No, if you already looked at UVLE, meron na rong official material that has been released by the handler in charge of this module. No? So hindi talaga ito part ng course, no? But I thought I'd give you a small or a short introduction into the structure of the MOS transistor for you to appreciate it a little bit better. No? If you want, later on, you can disregard this particular part of my synchronous session because this is not, like I said, this is not really part of the coverage. So just to give you an idea about the MOS transistor structure. Okay, so let's say we have a semiconductor material. Let's look at it from top view. So let's say this is my semiconductor. Let's say this is a P-type. Okay. And let's say in this P-type semiconductor, remember this is top view, we fabricate some N-type islands. So let me show that this way, no? Okay, so these are N-type islands. So if you will recall, I explained the difference between P-type and N-type when we're discussing the BJT. An N-type semiconductor, the charge carriers are negative or electrons. In a P-type semiconductor, the charge carriers are positive. Anyway, so just to illustrate the N-type islands better, let me color it green. Okay, let's take a cross-sectional view. Okay, so cross-sectional view. where do I want to get my cross-section? Dito ko kukunin yung cross-section. So cross-section here. Okay, so this is what it will look like. So again, this is P-type. My islands actually will not go all the way to the bottom of the semiconductor. Yung islands ko, hanggang dito lang. So again, these are N-type. No? Maybe I should label them. No? So this is N, and this is also N. So this is N, and this is also N. Okay, between my two islands, I'm going to deposit an insulating layer. Okay, this is going to be my insulating layer. Insulating layer. And usually this is silicon dioxide. Actually, silicon dioxide is a form of glass. No? Silicon dioxide. So if I looked at that from top view, my insulating layer is here. No? So this is my silicon dioxide. Okay, and then on top of the silicon dioxide, I'm going to put a metal layer. So dito magkakaroon ng metal layer. So this is metal. Yung insulating layer yun, no? Yung nasa baba. Yung metal nasa taas. No? So the metal dito, I'm going to show the metal this way. So yung metal nasa taas ng insulating layer. Then I'm going to have a metal layer here too, and a metal layer here too. But the purpose of that is just for contacts. So dito lalagyan ko ng contacts. So this is how I access these particular terminals. Itong terminal na to, I'm going to call this S. This terminal, I'm going to call this G. And this terminal, I'm going to call this D. And S stands for source. G stands for gate. And D stands for drain. I'm actually going to have another terminal here. And this is B. And B stands for the bulk. The bulk is just the bulk of the semiconductor. Kaya tinawag na B. This is the bulk of the semiconductor, or the body of the semiconductor. Okay. If I take a look at this portion, pag tinignan ko tong portion na to ng circuit, you're going to notice I have a metal layer. Underneath the metal layer, I have an oxide layer. And underneath the oxide layer, I have semiconductor material. This is semiconductor material. So you have a metal layer. Okay, you have an oxide layer. And you have a semiconductor. And that's why you call it That's why you call it your Mos transistor. Because the middle of the structure of the Mos transistor is a metal, then an oxide, and a semiconductor. Or you have an oxide sandwich between a metal and a semiconductor. Later on, when you study capacitance, you're going to recognize this as the structure of a capacitor, where this is the top plate of your capacitor and the semiconductor is the bottom plate of your capacitor. But that's going to come later on in your other courses. Okay, so this is your MOS transistor. So how does it work? Okay, let me draw it again here. Okay. So these are my islands, my N islands. This is my oxide. This is my metal. Then I have metal here, I have metal here, metal here. And then this is my S. This is my G. And this is my D. Okay. S, G, and D. And this is my B. So this is P, this is N, this is N. Let me just replicate this. I just want to replicate it. What will happen if I connect? Let me use another color. What will happen if I connect a voltage between my drain and source equal to this? Let me call this VDS. So VDS is the drain to source voltage. What will be the value of I sub D? Can anybody make a guess? What will be the value of I sub D? If I just connect a voltage between my drain and source. Any guess? Any guesses? Walang gustong maghula? Dali naman maghula eh. Okay, so there's a brave person, si Ivan, sabi niya 0. Bakit 0, Ivan?
Sir, kasi wala pong path. Kasi nasa semiconductor po yung parang most ng connection nasa semiconductor.
Okay, ang sinasabi ni Ivan, walang path, no? In other words, walang pagdadaanan yung current dito. Well, in a way, you're correct, no? But to be more precise, bakit walang path? Okay? Remember that this is P. This is N, this is P. So you have a PN junction here, no? And then this is P and this is N. You also have a PN junction there. No? So actually, what does this look like? No, this looks like I have VDS. Okay. So meron akong PN dito. So this is PN. Remember, this is N, no? This is P. And I also have a PN here. And this is N. Okay. So what is this, no? You have two back to back. diodes. Pwede ba dumaan ng current dyan? Di pwede, no? Whenever you have two diodes na magka-contra, okay, then you cannot have current that flows. Okay. Anyway, you had si Ivan had a good a good sense of it, no? Wala kang path. Wala kang path. And the reason why walang path is because of this. No? Dahil meron kang dalawang diode na opposite in direction that is connected in series. Okay? Now, this was the slide I duplicated, no? So meron tayong VDS dito, no? So this is VDS. Okay, what will happen if I apply a voltage this way, no? So okay, what will happen if I apply a voltage that way? Okay, by the way, no, usually itong bulk is connected to ground and the source is also connected to ground, no? Not always, no, but usual case, the bulk is connected to ground and very often the source is also connected to ground. So that the voltage between G and B is also the voltage between G and S. So let me call this VGS. Ano mangyayari? Okay, yung metal dito is going to be at a positive potential with respect to ground. In other words, there's going to be an electric field in this area. No? The electric field will be in the direction from negative to positive. No? Or you might think of it this way. No? Since this is connected to the positive terminal of VGS, this looks like a positive plate. So this looks like a positive plate. So let me just put positive here. No? Now this is a p-type. But just because it's a p-type does not mean there are no electrons in this particular material. Meron ding electrons yan. It's just that ang nagdo-dominate are the positive charge carriers. Now, the positive charge carriers are plentiful. Talagang madaming-madami. Yung electrons, bahagya lang. But just the same, the electrons that are in the p-type will be attracted to the positive plate that is here. No? So if you take a look, yung mga electrons, let's say these are electrons, they will all now tend to travel here. They will all try to travel here. All the electrons will go there. And what will happen? What will happen is, all of a sudden, because all the electrons went here, this will also become N-type. So this particular area becomes N-type. So originally it was P-type, but because all of the electrons went there, this area becomes N-type. But that happens when VGS is greater than or equal to a certain threshold voltage, VTH. Don't mistake this to be Thevenin voltage. No? VTH here stands for threshold voltage. So VTH, this is called the threshold voltage of the Mos transistor. And this is a parameter of the transistor. Meaning to say, pag tinignan mo yung datasheet ng transistor, for example, sa internet, doon makikita mo kung ano yung threshold voltage nung transistor na yan. Ano? That's a parameter of the transistor. Okay, so now, ice of D can flow. Right? Ngayon, pagdating dito, parang meron kang layer here, where it can flow. Because now, this looks like just one material. No? Itong N-type dito, looks like this N-type here, looks like this N-type here. So in effect, this looks like, in effect, like a resistor. So ice of D, so if VGS is greater than or equal to VTH, ice of D will be greater than 0. Okay? Itong area na to, let me use a different color. No? Sige. Itong area, nagiging magulo yung drawing ko. No? This area, you call this a channel. In fact, you call this an N channel. So you now call this an N channel Mos transistor, or in short, you call it an NMOS transistor. Okay, that is called an NMOS transistor. So that's how the MOS transistor works. Without any VGS, current cannot flow. Current cannot flow here because you have two back-to-back diodes in effect between this N, the bulk, and this N. But when you apply a VGS, if that VGS is greater than a particular threshold voltage VTH, you are going to enhance this particular area. Okay, that's what that's the technical term. No? It's an enhanced channel. You're going to enhance a channel into this particular area. So this is going to be a continuous N section, and now current will be able to flow. Are there any questions so far? Okay, that's as far as I want to go in the physics. No, in fact, that's not really physics. It's really very, very qualitative. Okay, like I said earlier, this is not part of the material of the course. I just wanted to mention this to give you a better appreciation of how the MOS transistor works. No? If it was above your head, if you feel that it's confusing you more, then you can forget this part of the synchronous session today and focus on what I'm going to explain from this point onward. So before I proceed, any questions? May mga tanong ba? Okay, so what do I want to do next? Okay, let me show you how ice of D will vary with VDS, okay, with a certain VGS applied. So going back here, so meron akong VGS that is greater than VTH. How will ice of D vary with VDS? Ano mangyayari sa VDS, for example, sa ice of D, for example, if I increase VDS starting from 0? No? So we assume VGS is greater than VTH. Siyempre, pag VDS equal to 0, walang ice of D. No? Because there's no potential difference between your drain and your source. As I increase VDS, expect ice of D to increase. No? Because this area is acting like a resistor. So this area is not a perfect short circuit. No? This will act like a resistor. Therefore, the greater the voltage, the greater the current. And that will continue. It's not going to be a linear resistor. There's going to be a slight curve. So it's not going to be a perfect straight line. A perfect straight line would make it a linear resistor. At some point, increasing VDS will not increase ID further. So at some point, this will become flat. So, pangit yung drawing ko ng konti, no? Let me try to fix it. So at some point, this will become flat like that. So I have here several modes of operation. Okay. This mode of operation, I call this the linear mode. Okay. Between your drain and source, it is like a resistor. So like a resistor between D and S. Okay, note here that in the linear mode, ID is a function of VDS. This is in the linear mode. Okay, this mode of operation is called your saturation mode. And note that ID is not a function of VDS. Kahit na anong value ng VDS, pareho yung value ko ng ice of D. Now, when does this happen? Saturation happens when VDS is greater than or equal to VGS minus VTH. Okay? In other words, going back to this, habang linalakihan ko itong VDS, lalaki itong value ng ID. But at some point, if I make this become any bigger, ice of D will already become constant. Now, why does that happen? Again, I don't want to get into the physics. I'm just going to mention this. This value of VDS actually has an effect on the electric field here. It doesn't seem so, but it does. So the larger the value of VDS, the smaller this electric field becomes. At some point, the electric field will become almost so small that your current will no longer increase. So yun yung rason kung bakit at some point nagiging constant na to. That's as far as I want to explain it. You're going to learn the real explanation when in your future semiconductor physics courses. So saturation happens when VDS is greater than VGS minus VTH. In fact, when this happens, ID is just K, a constant K, times VGS minus VTH squared. your ID will just vary with the square of the difference of VGS, the gate to source voltage, minus your threshold voltage. Okay. On the other hand, in the linear region, your ID is a function of VDS. No? In fact, ID is equal to 2K VGS minus VTH minus VDS over 2 multiplied by VDS. VDS over 2 multiplied by VDS. And this happens when VDS is less than VGS minus VTH. So doon ang shift, no? From linear to saturation. So at some point here, the transition from linear to saturation, this is when VDS is equal to VGS minus VTH. No? Maybe I should say this is greater now. Greater. So it's in saturation when VDS is greater than. Sorry. It's in saturation when VDS is greater than VGS minus VTH. It is in linear when VDS is less than VGS minus VTH. And the transition is when it is equal. When it is equal. So that's somewhere there. Okay. Now what happens if I make my VGS smaller? No? So but I'm showing a graph assuming that VGS is greater than VTH. What if I chose a smaller VGS? Well, my curve is just going to shift lower. No? So let's say this is VGS1. So this will be VGS2, where VGS2 is smaller than VGS1. Sorry, VGS1. This will be VGS3. Which is less now than VGS2. Now remember that you have to satisfy this condition. That VGS has to be greater than VTH for any current to flow. Okay. And so this is your linear. You might think of this as your linear mode. And then this is now your saturation mode. Are there any questions so far? Any questions? Are you still with me? Buhay pa ba kayo? Okay, just to make an analogy between the BJT and the Mos transistor. Okay, sige, just as a review. Ano yung operating modes ng BJT? Can someone shout it out? What are the operating modes of the BJT?
Ano po, sir? Forward active, cutoff,
Okay.
and saturation.
Okay, so BJT, meron tayong tinatawag na active, meron tayong tinatawag na cutoff, at saka saturation. So sa BJT, active siya when pag parehong reverse bias yung collector base and forward bias yung emitter base, ano? And your formula is IC is equal to beta IB. Cutoff siya pag your base current is less than 0 or your VBE is less than the forward voltage, no? And saturation pag parehong forward bias. So this is just a review, no? Okay, anong katumbas niyan sa MOS, no? Sa MOS, ang katumbas ng active sa MOS is actually saturation. Okay. Why? In the BJT, in the active region, your collector current is not dependent on your collector to emitter voltage. No? That is the saturation region for MOS. Ngayon, yung cutoff sa MOS, meron ding tinatawag na cutoff. And this happens when VGS is less than VTH. When VGS is less than VTH, wala kang channel. Wala kang induced channel, and therefore there is no current that flows. So yan yung katumbas ng cutoff. Tapos yung parang saturation sa BJT, ang pinakamalapit sa MOS is your linear region. Yun yung pinakamalapit dito sa MOS. Okay? So these are rough comparisons between the BJT and MOS, no? So yung active region sa BJT is equivalent to the saturation region in the MOS. And this is where, well, it's funny because if you think of the MOS as a linear device, the MOS is acting as a linear device when it is in the saturation region, not when it is in the linear region. So that might sound a little confusing to you, no? But when you use your MOS as a linear device, that is like when you use it as an amplifier, it has to be operating in the saturation region, which is by comparison the active region in the BJT. Pag tinignan nyo yung curves ng BJT, I did not discuss the curves of a BJT, but the BJT curve, no, BJT curve would be a plot of IC, VCE, very similar, no? Looks like that. Where this is your active region, and this is your saturation. And these are the different values of IB, no? So this is IB1, IB2, which is less than IB1, IB3, which is less than IB2, no? And now this would just be equal to beta times IB2. This is just beta times IB2, this is IB3, no? So this is sa BJT. We did not really discuss this, but if you compare this to this, you're going to see that yung saturation dito, ang katapat niya rito is yung active region. So I hope that does not confuse you. Okay, so this is the circuit symbol for your N-channel MOSFET. So this shows 4 terminals: the drain, the gate, the source, and the bulk. Now sometimes the bulk is connected to the source. So just like what we did here, no? I connected my bulk to the source. So bulk is connected to ground, source is connected to ground. In effect, the bulk and the source are connected to each other. And when that happens, then you can make this your default symbol. This can be the default symbol for your transistor. Now, it's not always the case, no? Sometimes by default, the bulk is connected to ground, but the source is not connected to ground. No? So when you see this just implies, no? This just implies that the bulk is connected to maybe I should change this. Let me change the slide. No? Implies that the bulk is connected to ground. No? This is more correct. Mas tama ito. Implies that the bulk is connected to ground. So pag nakita nyo to, ibig sabihin the bulk is not connected to anything. Pag nakita nyo to, it implies that the bulk is connected to ground. Okay, there's another type of transistor which is called your Pmos. So this is P channel. And the circuit symbol is quite similar. Now this is your drain, your gate, your source, but this time the arrow is pointing this way. So the arrow here implies the direction of current at your source terminal. No? So the direction of current here is flowing out of your source. Here the direction of current is flowing into your source. In your P channel, ang mangyayari lang, your bulk is N, your islands are P, and then all your voltages are reverse. And all your current directions are also reverse. So we're not going to discuss the P channel much. All of the concepts that are going to be introduced in this course are going to be introduced using the N channel. And in some later time in your EEE journey, you're going to be discussing the P channel. Are there any questions? So this is just to summarize the operating modes. No? By the way, let me go back to this. Can somebody tell me ano yung value ng current na to, IG? At steady state, no? At steady state. After this circuit has stabilized, what is the value of I sub G? Can someone tell me, or can someone guess? Any guesses? Somebody says, si Mark, ano yung sagot mo, Mark? Can you shout it out? Eyes of D? Eyes of D ba yung sinabi mo? Yeah, nice try, no? But yung eyes of D, dito umiikot, ano? Dito umiikot. So wala namang path from here to go back here, ano? So it's not eyes of D, but it's a good try. Anyone else? Anyone else? Okay, what did we say was this black material? What is it? Do you remember? No? This black material is an insulating layer. If it's an insulating layer, ibig sabihin, okay, if these are DC, if these are DC voltages, if this is a DC voltage, ibig sabihin I sub G is equal to 0. Kasi paano siya tatagos dito sa insulator na to? No? In other words, hindi pwede mag-flow yung current this way. No? Current cannot flow this way because you have an insulating layer here. Okay, do you understand that? So I sub G is equal to 0. Now that's true, but that DC steady state. No, later on you're going to study the concept of displacement current, And you're going to see that even if that's an insulating layer, there's actually a current that can flow, but it's not a conducting current. It's a displacement current. But for now, DC, IS of D is equal to 0. So when VGS is less than VTH, IS of D is equal to 0, that's your cut off. No? And then these are your conditions for linear, and then I already presented this equation. And these are your conditions for saturation, and I already presented this equation. No? So for all modes, IG is equal to 0. Actually, if IG is equal to 0, ID must equal to IS of S. Why? No? Remember that this will follow KCL. If that follows KCL, then that means that IG plus ID is equal to IS. No, naalala niyo yung transistor naman ID plus IC is equal to IE. So dito IG plus ID is equal to IS. Pero sinabi natin that IG is equal to 0 and therefore ID will always be equal to IS of S. Kung ano man yung current na pumapasok sa drain, yun din yung current na lalabas sa source. No, hindi kagaya ng transistor. Yung transistor, there's a slight difference between IC and IE. Depending on the beta of the transistor, that difference becomes smaller, no, as beta becomes bigger. Pero sa Mos transistor, ID is equal to IS because IG is equal to 0. Now, what is the other advantage of IG being equal to 0? If IG is equal to 0, that means that anything connected between gate and source will not be delivering any power. And that's what makes the Mos transistor a very powerful device, no? Because you can control it without having to spend any power or hardly spending any power. That's why circuits that are composed of Mos transistors are very low power circuits. That's what allows, for example, your cell phones to last for 10 hours without recharging, because most of the circuitry inside there is composed of Mos transistors, and they consume very little power dahil dito sa IG being equal to 0. So what are our models? How do we represent our transistor? So if it is cut off, VGS is less than VTH, it's just open circuit everywhere. Now, just a warning, just because it's open circuit does not mean that VDS is 0 and VGS is 0. No? Kapag open circuit, meron pa rin yung value ng VDS at saka VGS. Okay. Kapag linear, okay, so these are the conditions for linear, it's equivalent to a resistance. Now, what is the value of that resistance? If this is your curve, no, ID versus VDS, for a particular value of VGS, I have a curve. Okay. So this is for a particular value of VGS. The value of your resistance is approximately equal to the slope of this line. No? Actually, it will vary with VDS, no? Because this is not exactly a straight line, this is a curve. But whatever slope of this line, that's the approximate value of RDS on. So this is the slope is approximately equal to RDS on. So in the linear mode, your Mos looks like a resistor. And finally, in saturated mode, what does it look like? Your Mos looks like a voltage-controlled current source. So this is a current source. It's a controlled current source. What controls the current source is this value VGS. And I already gave you the equation. ID is equal to K multiplied by VGS minus VTH squared. Okay. Any questions? Any questions so far? Okay, so here I try to outline, these are in my own words, the basic steps in analyzing a MOSFET circuit. Okay, so I try to outline in more detail than your notes. Ano? So what is the first step? The first step is to determine VGS. How do you determine VGS? It's very easy because I sub G is equal to 0. In other words, whatever your MOS transistor is connected to, it will not have any effect on the voltage of that particular circuit because it does not draw any current. So I can easily compute for VGS. Okay. And if VGS is less than VTH, then I already know that the transistor is cut off and ID, which is equal to IS, will be equal to 0. Okay, now if we see that the transistor is not cut off, pag nakita natin na yung VGS is greater than VTH, we start with the assumption that the transistor is saturated. So if you compare this to BJT, ano yung lagi nating unang assumption sa BJT? We always start with the assumption that it is active. And then when we finally solve for the values that we want to solve, we just have to check whether active talaga o hindi. So dito sa MOS transistor, ang unang assumption natin is it is saturated. So we use this formula to determine the value of ID. Now, after solving for ID, we solve for VDS. How do you solve for VDS? You apply KVL to the drain to source path. Just like when we solve for VCE in a transistor, we apply KVL from the supply to the supply to VCE path, the supply to ground path. So same here, no? So after solving for VDS, we just have to check our assumption. We compare VDS to VGS minus VTH. If we see that this is greater, then the assumption is correct. Yung kinompute nating ID using this formula is correct. If we see that it is less, then we know that the assumption is wrong. The transistor must be in linear mode. And this is the correct formula now for ID. Unfortunately, if we use this formula for ID now is a function of VDS. No? Di kagaya dito, ID is not a function of VDS. So you're going to end up having to solve two equations in two unknowns because you're going to have to combine this with the KVL equation of the drain to source path. So let's take an example. So this is similar to what I did when we discussed BJT. Okay, I have a very simple circuit here where my input is actually VGS. And I have a drain resistor and my output is actually VDS. So my input is VGS and my output is VDS. So for these values of input, I'm asked to compute for I sub D and I'm asked to compute for V out. I'm given these are transistor parameters. So these are set for the transistor during the fabrication process, depending on the requirements of the depending on the design requirements, for the particular transistor. So the problem is determine ID and V out. Then I have a second question here. At what input voltage is the transistor at the transition from saturation to linear? So let's try to solve for some of these values. Okay, let's start with the easy ones. Okay, shout out na lang kung sino mga matapang. What is I sub D when Vin is equal to 0? Anyone? Come on, no? I want you to think. What is I sub D when Vin is equal to 0? Anyone? Come on. Okay, isa lang yung matapang, si Ivan. Bakit 0, Ivan? Can you just shout it out?
Sir, ano po, less than VTH po yung VGF.
Exactly, no? Because V in is less than VTH, so naka-cut off siya. So I sub D is equal to 0. So kung 0 yung I sub D, ano yung V out? Iba naman, no? Let somebody else answer. If I sub D is 0, what is V out? So I have an answer from Patrick, and his answer is correct. This is going to be 12 volts. Bakit? No? If I sub D is equal to 0, wala kang drop dito sa R sub D, so ang VDD mo will be equal to V out. Okay, next, 2 volts. Anong value ng I sub D? Okay, can I hear somebody else? What is the value of I sub D? 2 volts.
0.
What is that, Cedric?
0.
0, no? Because V in is still less than VTH. Mas maliit pa rin yung VTH. So naturally, ang V out will still be equal to 12 volts. Okay, ngayon, iba na yung situation dito, no? When V in is equal to 4 volts, that's already greater than 3 volts. No? So here, V in, which is VGS, is greater than VTH. So don't expect I sub D to be 0 anymore. Okay, so let's compute for I sub D. So for V in equal to 4 volts, so what do we assume first? Our first assumption is always assume that it is saturated. So if we assume it's saturated, I sub D is equal to K VGS minus VTH squared. So that's equal to 0.25. No? K is 0.25 MA per volt squared. So I'm going to want my I sub D to be in MA. So I'll just retain this, 0.25 MA. What is VGS? VGS is 4. VTH is 3. No? So this is 4 minus 3 squared. So this is just going to come out 0.25 MA. So this is 0.25 MA. So what will be the value of V out? Someone? Anyone? Ano yung value ng V out? I want to hear the other people, please. What is V out? Sayang naman, nag-attend kayo ng synchronous session, but you're not really trying to keep up, ano? Okay, so somebody, who's this? Ira says 11.5, no? So, okay, so V out is equal to VDD minus IDRD, no? That's applying KVL to this particular path. No? So V out is VDD minus IDRD. So that's 12 minus 0.25 multiplied by 2. Okay, so this is 11.5 volts. Ngayon, hindi ko muna ilalagay dito. Bakit? Kasi i-check ko muna kung talagang saturated. I-check ko muna kung talagang saturated yung transistor, no? Because I can only use this formula for I sub D if it's really saturated. Now, how do I check? So check, no? What is our check? Our check is VDS should be greater than VGS minus VTH. No? What is VDS? VDS is 11.5. And that certainly is greater than 3 minus 4 minus 3. So check yan. Right? So because of this, I know that it is saturated. So it's confirmed that saturated. Okay, and so tama, no? Tama yung sagot ni Ira. This is 11.5 volts. Okay, can someone compute it on your own, no? Give you about a minute. Hindi naman ganun katagal. Can someone fill in the data for 6 volts? So try to compute it on your own, please. And then shout it out to me. Okay, 2.25 MA. And 7.5 volts. Sino yung sumagot nun? Si Daniel. Daniel, did you check whether it was really saturated? Daniel, chinek mo ba na talagang saturated? But it's very easy to check, ano? You just compare VDS to VGS minus VTH. What is VDS? VDS is 7.5. VGS minus VTH is 6 minus 3, so that's 3. No? So it's not 6 minus 3, ano? It's not 5, no? So 7.5 is greater than 6 minus 3. So tama, it's really saturated. It's really saturated. Okay, let's do this next one together. Let's do this next one together. Yung 8 volts. So Vn is equal to 8 volts. Again, I assume saturated. So I sub D is equal to 0.25 times 8 minus 3 squared. And what is this? I have it somewhere. No, this is 6.25 MA. Okay, I compute for V sub D, which is 12 minus ID times RD. And if I compute this, so this is 12 minus 6.25 times 2, and I'm going to get minus 0.5 volts. Teka, no? Bakit ito minus? Pag may nakita kayong minus, magduda na kayo. Because there is no negative supply in this circuit. No? Usually one possible way of getting a negative voltage is if there's a negative supply in the circuit. The other way is maybe sometimes when you have capacitors in the circuit that have stored voltages, then some of that voltage might add up in the negative direction. Ano? But anyway, this is minus. So yung palang minus, nakakaduda na. No? So this is already doubtful. But anyway, just to check, no? Sorry, this is VDS, no? VDS, not VD. VDS greater than VGS minus VTH? No, definitely not, no? Because 0.5 is not greater than, what is it? 8. Sorry. Sorry about this. 0.5 is definitely not greater than 8 minus 3. This is wrong. So obviously it is linear. So ano ngayon kung linear? My correct formula for ID is ID, okay, is equal to 2K VGS minus VTH minus VDS over 2 multiplied by VDS. So this is 2 times 0.25. VGS is 8. VTH is 3. Now I don't know VDS, so that is a variable. This is one equation. Naging komplikado ngayon yung buhay ko kasi nasa linear mode siya. So yung ID ko ngayon is also a function of VDS. It's not only a function of VGS, but it's also a function of VDS. However, I can form a second equation from KVL here. I have VDS is equal to VDD minus ID RD. So this is equal to 12 minus ID times 2. This is my second equation. And I can solve this simultaneously. Unfortunately, it's not easy to solve this simultaneously. You come up with something quadratic. No? Because here you have a VDS squared. No? Pag minultiply mo itong dalawang term na to, meron kang VDS squared. So actually, itong relationship na to, if I substitute for how do you say it? For ID in terms of VDS into this equation, or VDS into ID in terms of ID into this equation, I'm going to get a quadratic equation. Fortunately, your calculators can solve that. Gamitin lang niyo yung solve function ng calculator nyo. Or even your quadratic function, your calculator can solve that. So anyway, what is the solved solution? Okay, let me check my notes. Okay, I'm going to get, let me see. Yeah, here. I'm going to get ID. So the solution, ID is equal to 4.73 MA, and VDS is equal to 2.53 volts. So this is 4.73 MA, and this is 2.53 volts. Okay, we don't have any more time, so I'm going to let you do this too. At the same time, I want you to think about this. No? At what input voltage is the transistor at the transition from saturation to linear? So alam natin dito nasa saturation tayo. Alam natin dito nasa saturation tayo. Tapos dito sa 8 volts, biglang naging linear. So somewhere in between these two, there's a transition. There's a transition somewhere in between these two from saturation to linear. So I want you to solve for that. No? Now the other transition is from cut-off to saturation. Kasi ganun yung operating mode. Ano? First, it's cut-off dito, cut-off dito. Dito naging saturation. At what point siya nagta-transition from cut-off to saturation? Obviously, that is when Vn is equal to VTH. When Vn is equal to VTH, almost always, in fact, always, your VDS, as long as your VDS is not 0, your VDS will be greater than VGS minus VTH, because VGS minus VTH will be equal to 0. So that would be your transition from cutoff to saturation. So that's going to be at 3 volts. Now, between these two, there's going to be a transition from saturation to linear. So solve that and solve for this. And we're going to continue the discussion next time. Are there any questions? Any questions?
Sir, hello po.
Yes, please.
Sir, yung question ko po with regards po dun sa recent na problem set po.
Okay, sige.
Sir, pwede po ba namin i-assume na IC is equal to IE sa problem set?
Uh,
As long as we state it po sa solution namin.
Pwede siguro, ano? I don't know how the checker is going to, or hindi ko kasi alam kung ano yung instruction ng handler sa checker when it comes to that, ano? Kasi para sa akin, para sigurado, you can do it more exactly, di ba?
Okay. Kasi yung sa ano po kasi, sir, experience po kasi dun sa quiz. Tinatanggap naman po yung assumption na IC is equal to IE. So, tumatama pa rin po yung sir.
Yeah,
So,
actually, if you take a look at the lecture of si Dr. Sison,
yes, sir.
parang embedded naman talaga sa lecture niya, sinabi niya that IC is approximately equal to IE, no? So, baka tinatanggap niya na you can make that assumption, no? But you just have to be careful because that is really only true pag mataas yung beta. No?
Ano,
So pag
sir?
yung
Okay.
IC is approximately equal to IE is really true pag mataas yung beta, di ba?
Yes, sir.
Because IC is equal to IE times beta over 1 plus beta, no? So pag mataas yung beta, that is true. Pag mababa yung beta, it's not that true, no? It's not that true. And may mga transistors, yung mga power transistors na hindi ganun kataas yung beta. So you just have to be careful, no? Just have to be careful. So pwede mong gamitin yung assumption na yan kung more or less alam mo na mataas yung beta.
Okay, sir. Sige po. Thank you po. I-gamitin ko na lang po sa yung beta kasi since explicitly stated naman po sa problem set.
Yeah. Pero yeah, you're right na pag ginawa mong equal, mas madali talaga i-solve yung problem pag ginawa
Yes,
mong
sir.
equal.
Okay. Thank you po, sir.
Okay. Any other questions? Any other questions? Yeah, going back to that question about IC approximately equal to IE. I guess sa totoong buhay kasi, yung error that might introduce might already be within the tolerance also of the transistor, no? That's why yung mga rule of thumbs ng mga designers, usually pag mataas yung beta, ginagawa na lang nilang equal yung IC at saka IE. Kasi hindi din naman talaga eksakto yung mga parameters ng transistor, no? So that's why that assumption is also used quite a lot. So anyway, if there are no more questions, I will stay logged on just in case there are any more questions that you might think of. I will turn off the session when the last person logs off.